So this is the image taken of the Whirlpool Galaxy by one of the telescopes outside, and I'm sure it's a lot of effort, but it looks like a blob. Why does the radio image look so much worse than the optical?
In general, radio images are lower resolution than optical images. Basically, the shorter your wavelength, the higher resolution, and
Okay.
the larger your telescope, the higher your resolution.
So the radio telescopes pick up longer wavelength radiation, so if I have the same size telescope, I get a worse image.
That's right. So we're looking at 2 centimetre radiation here. So compare that to optical, which is a few hundred nanometres. That's, I don't know, 1,000 times smaller. So to get the same resolution as an optical telescope, you'd have to build a radio telescope 1,000 times as big, which is just not physically possible.
Okay, so that's the explanation for its blobbiness. But what do you see here? As a radio astronomer, what can we tell about the galaxy from this image?
If you looked at a really compact source, like a star that you didn't resolve at all, you would see a smaller blob than this. So given that I know what a compact source should look like, I can see that this blob is bigger than that. So it is extended relative to the beam of the telescope.
So we're seeing some of the galaxy,
We're seeing,
rather than just a point.
That's right, yeah. So we're definitely seeing an extended source here. You can also see that it's elongated towards the top. So that's a bit of the companion that we're seeing at the top there.
So you said this is an image from the small array.
That's right.
Which is the low resolution end of things. There's a large array as well.
There's a large array as well. Right, so we can go to the image from the large array.
Okay, now that's better. I can see there's the central blob, but are those the spiral arms, maybe?
Yep, that's right. So you can see the spiral arms here. They're not as bright as they were in the optical.
But only in patches. It's not a complete spiral arm at all.
That's right. So that highlights the difference that we see when we look in the radio compared to the optical. So when we look in the radio, we are looking at sites of active star formation, really. So what we're seeing here is that there is more star formation going on in these bright patches than there is in the dimmer parts of the spiral arms.
So that's what we can get from here. We can learn a lot about the galaxy from that. But what about other radio telescopes? There are other things we can see.
That's right. So you can also look at the distribution of gas in the radio, and you can do that by looking at very specific radio frequencies. So here's another image, this time taken with the very large array in the States. And this image is made at a very specific radio frequency. It's made at 21 centimetres, and that is tuned to be exactly the right frequency to catch electrons transiting between different spin states in neutral hydrogen.
So it's a way of tracing where the hydrogen is in the galaxy, and that's
Exactly.
the fuel for star formation.
Exactly, yeah. So you can see it's quite even throughout the whole galaxy. It's not.
And it extends beyond the galaxy as well. This disk is sort of stretched out beyond the optical disk as well.
That's right. And there's this lovely great big tail of neutral hydrogen, which you don't see in any of the other wavebands, which is probably caused by the passing through of the companion.